Hi everyone. In this video we're going to look a little bit closer at the structure of those hydrocarbons. Let's look at the alkanes. We're familiar with the fact that alkanes consist only of carbon-carbon single bonds. And so if we use our bond line structure and draw out the zigzag pattern, so we have 4 carbons here. So this would be C4H10. Following that CnH2n plus 2 general formula for a completely saturated hydrocarbon where there are only single bonds. We can add wedge and dash bonds to this to give it more of a three-dimensional appearance. Remember that the wedges are coming out of the board, the dashes are coming into the board, so we start to see a little bit more of how this will actually look in three-dimensional space. Because this carbon atom has 4 groups attached to it, the ideal bond angles will be 109.5 degrees for that tetrahedral molecular geometry. And these in an alkane will be pretty close to that angle of 109.5. You'll just see small deviations here and there. There is free rotation about all single bonds. So if you were to, say, twist this around and get something like this, then that would be identical. It's a different conformation. We have just rotated about this central bond there, and all of the bonds have rotations. Okay, so there's an infinite number of conformations that, if we spin around that bond, we could just stop, whatever, getting an infinite number of conformations there. Some, of course, are more stable than others, so most of the time the compound will actually exist in this conformation, which we call staggered, but that's not something we're going to focus on here. All of the carbon atoms in an alkane will have that tetrahedral molecular geometry, giving rise to the bond angles of 109.5 degrees. And in terms of hybridization, the carbon atoms having 4 substituent groups must be sp3 hybridized. So there would be overlap in, say, this carbon-hydrogen bond of an sp3 orbital from carbon and an s orbital from that hydrogen. And those are going to form that covalent bond. If we look at this bond over here, it's a carbon-carbon bond, so it's going to be sp3 orbital overlap to form that sigma bond. Now let's move on to cycloalkanes. Cycloalkanes, like alkanes, will have carbon-carbon single bonds, but because the 2 ends of the straight chain are tied together to form a ring, there are 2 fewer hydrogens. So the generic formula for a cycloalkane is CnH2n. This makes a cycloalkane unsaturated because it doesn't have the maximum number of hydrogens possible. So these hydrocarbons will form rings. The smallest size is 3, increasing by 1 to 4, 5, and 6. These are the examples that I'm going to show you. We represent these by the polygons. Okay? And again, this is not exactly what we would see in 3 dimensions. We can use the wedge and dash to help us visualize this. But these all have kind of a distinct conformation, and the 6-membered ring to me is most interesting. It actually is what we call a chair conformation. So this is more or less what it would look like in 3-dimensional space. And we have these hydrogen atoms coming off of each vertice as such. Okay, so I won't draw them all in, but there are more there than I have drawn. But this is the 3-dimensional shape of the cyclohexane. And here's a ball and stick model to give you a better idea of what that looks like compared to what I've drawn on the page. The 5-membered ring is what we call an envelope. And going down to 4, this is not going to be a flat square. We like to think of it as puckered, and that is due to the fact that we don't want the bonds to overlap. So these bonds on neighboring atoms, if they're kind of overlapping in the same space, they are going to be at higher energy because of the electron-electron repulsions in these bonds being close together. And they don't physically look close together here, but if you looked at a spaceflow model, it would be more obvious. So this adopts more of a puckered shape, as we can see in the three-dimensional picture. And for the triangle here, the cyclopropane ring, we will have a completely flat structure, and this will also have increased angle strain here, because we would predict, based on having 4 substituent groups on this, that the ideal angle would be 109.5 degrees. It's just not possible to have a 3-membered ring where the angle is 109.5. Those bonds would not be able to arrange themselves in this way. So we do have a smaller than predicted bond angle, which can be seen here by the polygon that we use. Same thing in the cyclobutane ring, 90-degree angles. And in our cyclohexane, it just is the most stable. There's the least strain there because the bond angles are as close to that 109.5 degrees as possible. In the cyclopentane ring, I believe the number is 111 degrees. So anyway, we do predict that the geometry about all these carbon atoms, because they are all containing those 4 substituent groups, would be tetrahedral, albeit there is some deviation from that ideal angle. And then all the atoms would be sp3 hybridized. Next, let's look at the alkene. Alkenes consist of carbon-carbon double bonds and have the general formula CnH2n. Note that this formula is the same as the cycloalkene. So if we're given a molecular formula that has this ratio of carbon to hydrogen atoms, it would not be possible to tell if it was a ring or a double bond without more information. So these alkenes having a carbon-carbon double bond will have different molecular geometry. So the carbon atoms involved in the alkene have 3 electron domains about them. And with 3 electron domains, we would predict a geometry of trigonal planar. And so these alkene structures are flat. And that means the bond angles here are 120 degrees. We would expect there to be slight deviations from this based on the fact that the double bond, having more electron density, would have an angle about it that is slightly greater than 120 degrees, whereas the angle on the opposite side would be slightly less than 120 degrees. But 120 degrees is a good estimate for the bond angles about a carbon-carbon double bond. And having 3 electron domains would make these sp2 hybridized. There are 2 bonds here. One is sigma, and that sigma bond is the end-on-end overlap of atomic orbitals. So we have an sp2 orbital and an sp2 orbital from those 2 carbon atoms. The second bond is a pi bond, and that's the side-to-side overlap of p orbitals. Okay? And the arrangement of the double bond can differ. So these 2 compounds, because the position of the double bond has changed, are known as isomers. The connectivity is different, constitutional isomers. And then looking at something like this, we have a new class of compounds. So there is not free rotation about carbon-carbon double bonds. That is locked in this conformation. So we can't simply rotate a bond like we did for an alkane to get to this structure. And these 2 compounds are known as geometric isomers. And sometimes you'll hear stereoisomer as a broader class of compounds that these would fit into as well. So geometric isomers differ in the arrangement of the atoms in space. So this group and this group are opposite one another. We call that trans. And these 2 groups are on the same side, so we call that cis. Cis-same. Okay? Trans, think like transcontinental, transatlantic, on opposite sides. So geometric isomers exist for double bonds because of that limited rotation about the carbon-carbon double bond. I will ask that you are able to recognize geometric isomers, but we won't go much beyond recognizing that that is the case. Alkynes consist of carbon-carbon triple bonds. And when we draw an alkyne, it's going to look slightly different from the zigzag pattern that we see for alkanes and alkenes. Because the geometry about a carbon-carbon triple bond is linear, the bond angle here is 180 degrees. So when we translate this type of structure to the bond line, we can draw it simply like this, where each end of my triple bond represents a carbon atom, and then we have the end of my chain which represents additional carbon atoms. And of course they would have met their valence requirements, so there are 3 additional hydrogens at each of those points. This would be an alkyne that is in the chain, an interior alkyne, and we could have a terminal alkyne that's at the end of the chain. So there is a carbon atom here and here. Okay? So keep in mind that we draw this to reflect the 180 degree bond angles of that alkyne. So, like I said, the geometry is linear, and the fact that there are only 2 groups attached to the carbons of the triple bond, the hybridization is going to be sp. And of course, the triple bond, as we're aware, is made up of 1 sigma, so that end-on-end overlap of atomic orbitals, sp and sp in this case. And then there are 2 pi bonds. We have them perpendicular to one another. The side-to-side overlap here, and the side-to-side overlap in the plane. So, alkynes are sp hybridized with 180 degree bond angles. The last structure I want to look at is that of benzene, and this is a specific type of hydrocarbon. It is one of those aromatic species that is especially stable. And we know that this is especially stable compared to an ordinary alkene because the reactivity profile is very different. So it takes a lot more harsh conditions to get the double bonds in benzene to react than an ordinary double bond in an alkene. So let's look at the structure here. Remember that there is resonance in benzene, and so I can draw a structure that looks like this. That is an equivalent contributor to that true structure, which is the hybrid, where there's electrons delocalized about the entire ring. And so as a consequence of this delocalization, all of the bonds in benzene are identical, meaning all of the bond angles will be identical, and so we won't have the situation where the double bonds take up more space, because the double bond's not here and here and here, it's spread out all over the entire ring, as this hybrid structure indicates. So the bond angles in benzene are going to be 120 degrees, and all of the atoms are going to be sp2 hybridized with that trigonal planar geometry. So benzene is a completely flat molecule, and we can see that from this ball and stick model where all of the atoms are in the same plane. So if you have any questions about the geometry of the various hydrocarbons, please let me know. They do follow the same rules as we saw for molecular geometry of other types of compounds before. So thank you for watching.